sometimes we'll have to go to a full sort of drop-in retrofit, and a lot of times we can capture the higher flow or the higher pressure with a retrofit. On the re-engineering, I'm conscious of the time, so I've got a lot. I'm going to go through it very, very quickly, so it's going to be a lot of photographs, but we follow the same process, and I'll talk you through that as we go. So re-engineering, we use the process of reverse engineering, but with reverse engineering we take it a stage further. Because we're a pump OEM, we've been designing and manufacturing pumps for 158 years, we can add value to the reverse engineering process, and we can make the pumps more reliable or change the duty. So we use a lot of these techniques, the reverse engineering techniques, when we're doing re-rates or upgrades. So again, these are all real life examples, case studies we've got, and the interesting thing is none of these case studies that we're going to talk about tonight are our pumps. These are not our pumps. Okay, now this is the scanner we've got. We've got a sort of fair arm type scanner, laser on the head, and this is us scanning the bearing housing. So we'll capture the geometry, the dimensions, and that'll create a wire mesh model, and then from that, our team in Bangalore, they'll create a SolidWorks 3D solid model, and then as soon as we've drawn the 3D model, we can start to redesign it. So if we've scanned an impeller, we've captured the impeller geometry, then we apply all our design tools, so we can actually redesign the impeller, redesign the diffuser, redesign the volume. So this is a process that we follow, just gathering all the data, and this cursor's still not working. I think I need to reverse engineer the cursor, upgrade it. This needs an upgrade. Right, PMI, positive material identification. We've got all the tools. Sometimes we get the pump data sheet, and that's fine, it'll tell us what the materials are. Other times it's obsolete equipment, we don't have any information on it, so we'll use our PMI instruments to get a positive identification on the material. And then again, this is us going through the process. We've scanned it, we've got our wire mesh, we start to do all the 3D modelling, and then we can apply CFD, computational fluid dynamics. Scott talked about it earlier. We'll apply all the external loading, etc., finite element analysis. We'll run all the models. And this is a process here where we've done the scan on the model. There's a model here. This is the scan here. And then we've done the drawing, manufacturing drawing. We'll make a pattern, and there's a raw casting there. That'll all get final machined, die penned. This is here, the scanning. These heat maps are basically where we've done a comparison between the scan and our 3D model, and this is our tolerance bands here. Whether it's a casting or a final machine part, we can set these tolerances. So green is within the tolerance, you know, the yellow, light blue, these are without. So that's either there's excess metal or there's not enough metal on it. So that's just a check. So this is one we did. Again, third-party pump. This was actually a Sulzer pump, North Sea. Sulzer, the OEM, told the end user that they needed a new pump, and then they came to us and we said, well, we can actually give you a new pump end. So we scanned all the parts, and this was cheaper than actually buying a pump end from Sulzer. These are all scanned, so we've manufactured them. So we've actually reverse engineered, re-engineered it. All the impellers, shaft sleeves, diffuser bowls. And again, this all goes through our own QA system. So as soon as we've scanned it, the procedure starts. We just follow it as if it's an OE pump. It goes through all the QA procedures. We hydro test, we dye pen, we do any ultrasonics. Vacuum pump, it doesn't need to be a pump. This is one we completely reverse engineered the internals. We kept the discharge suction end and the crossover, that was all kept. And there's a raw scan here on the left. On the right is the 3D solid model. Again, that generates all the drawings. And then this is us building up the new rotor. And then this is a big BB3. This was quite a comprehensive project that we did, and you can see the impeller totally scrap. There's nothing on that. But because we're a pump manufacturer, we're a pump OEM, we design and manufacture pumps, we design and manufacture BB3s, we were able to sort of regenerate the model or the shape, the geometry of the impellers. Even if that was a one stage, we can regenerate, once we do the scanning, the actual impeller. So again, we scan the casings, top half, bottom half, and then if it needed, if it's an upgrade or a rewrite, then we can apply the redesign on that, because we've captured the geometry, all the dimensions. And these laser scanners now, we can scan to 1.5 thou accuracy, so it's pretty accurate. Again, this shows you the damaged impeller. Again, it doesn't matter, as soon as we scan it, we can generate a model from that. As I say, we've got all the design tools, because we design impellers. I'm just trying to keep this going. This was on the seawater injection pumps, on the bearing housing. Redesigned, there's the thrust pads, the tilting pads, and the journal bearings. These were all scanned, re-engineered. So these are the new impellers. These are all our impellers. We generated a new section arrangement drawing, new parts list, and then we've done all the dynamic analysis. Scott was talking about that earlier. So we've done a rotor dynamic analysis on it. And this is, again, we do reciprocating pumps. We make them in America. But again, this was a competitor's pump. It was obsolete, but the client still wanted to go with the pump. So again, we went to site. This was all done at site. Scanned, did the scanning, did all the modelling. And this is the new pump here. And that's it. Just re-engineering, in summary, it begins with yourselves, customer consultation, gathering the data, very important. Sample component, again, it doesn't need to be a new part. We've done it before, we've scanned new parts, but most of the time we're scanning old parts. And that doesn't really matter, because we take the holistic view. If it's scanning an impeller, we'll scan the casing, we'll scan the diffuser. It is cost effective. Go back here. No. I'm trying to, still not working. So here we are. And then it can address any technical issues. Because we're an OEM, we can take all that on board if it's a bad actor, etc. And we can incorporate, as we talked about earlier, we can incorporate an upgrade or a rewrite into the solution. Re-engineering, it's not just copying, it's not just replication, it's all about adding value. We're very much value proposition. It's not cost, you have to look beyond the cost, it's value, it's what we can bring to the end user. Last thing, but very important, is training. We've got two very good agents in Kuwait, Khalid Parker and Kanar. Khalid, if you can stand up and give a wave so everybody knows. Kanar looks after us for the oil and gas, KOC, KMPC, KOTC. And then on the utilities, power, water, desalination, we're looked after by PSC, Petroleum Services Company. So that's from Chandra. Chandra, if you can stand up and give a wave, you're still, there is, yeah. So we're well looked after. Sanjit and I cover Kuwait, and so we deal with both Khalid and Chandra. But what we offer, we do a lot of training, and if you talk to VJ Nice, she might give you it for free. But we do a lot of training, and we cover a lot of subjects. And as the great Pele said, I know all you folk in here like your cricket, we like our football. I actually felt quite nervous coming here tonight, because Sanjit and I we're Kolkata Knight Riders, and I know all you guys are Chennai Super Kings. But no, we're football guys, but the great Pele said, success is no accident, it's hard work, perseverance, learning, studying, sacrifice, and most of all, loving what you do or you're learning to do. It very much ties in with the Tamil Nadu Engineering Forum that you talked about earlier. But part of that journey is learning. We're all learning. Every day is a school day in engineering, and this cursor's still not working. So these are all just a snapshot of the training modules that we can do. We can design a training program to whatever you want. There's quite a lot of modules in behind each subject, but you know, we do 610, 682, pump components, installation, commissioning. We do workshop training, we do site training, classroom training, that sort of thing. But again, training is very, very important to transfer the skills onto your engineers, whether that's maintenance or operation. So, I learned to read Tamil. Now, I hope that says Mika Nandri. No, it's been a great honour, and I'd like to thank your good selves, the Tamil Nadu Engineering Forum, for allowing Vijay, Gauri, Scott, Sanjit and I, because we've really, really enjoyed it. We were all looking forward to coming here tonight. It's fantastic what you've done tonight. I think you've got something really, really special. 27 years, which is fantastic, and well done. So, Mika Nandri. So if you've got any questions for Sanjit and I know we've run over the time, so sorry about that. Sanjit, you can answer all the questions.
Hello. This is Ganesh Kumar from KNPC MAB Refinery. I have a few questions with you. I'll start with one. Actually, you explained about the MTPF of 48 months. Actually, supposed to be 36 months as per the APA and send-up. Why you are committing to that 48 months MTPF? Is there any intention?
Yeah, well, what are you looking for a mean time between failure of 48 months or?
Actually, as per the APA 610,
Yeah.
36 months MTFF will be sufficient. Sufficient is accepted.
Yeah, I mean, our pumps, 48 months is, yeah, our pumps will run. If the operator, if the end user is looking after the pumps, we had that curve up earlier. If you're running at the sweet spot, if the operators know what they're doing and they're running at the sweet spot, pumps, not just our pumps, but pumps will run for decades. Now, we've had pumps at ADNOC, I went to see them myself, one of the water injection pumps, believe it or not, ran for 20 years without any maintenance. The other pump that they pulled ran for 9 years, and the only reason they pulled it was they just wanted to see the condition. So, I mean, if you're looking after the pumps, they'll look after you, you know, so yeah, you can have pumps running well beyond 10 years without any intervention. Again, a lot of it depends on the application as well, you know.
Yeah, I fully agree with you, but not happening to all the pumps. I'm telling about that specific that period mentioned in the APA is 36 months. But you have committed for 48 months in your slide. That's what I am asking. Right?
I mean,
in our refinery, we have thousands of pumps running without any issues. Only few pumps have frequent problems, and that we are addressing. Maybe process upsets, nor the NPSS. So many things are there. to get the failures in the pump failures.
Yeah. I mean, there's some pump manufacturers out there that are recommending that the client, the end user, overhauls the pump every 2 years. And these are big pumps, or big seawater cooling pumps, but we're telling the end user, yeah, well, you should be getting about 6, 7, 8 years out of these pumps before you overhaul them. Again, it's, you know, the end users are getting told different things, you know. Because it says it in the manual. Normally the manual will tell you, you know, when to do the first overhaul and that sort of thing. But again, there's a lot of end users out there that are getting 8, 9 years on critical pumps without any overhauls.
Okay, I will go to the next question. We are talking about the BEP, best efficiency point of 58. That as per the standard, you need to maintain 80 to 120% of BEP. As per the APA 610.
Yeah.
If due to sizing and costing, the economic reasons, so many pump manufacturers are giving 50 to 60% of the BEP. That means just away from the BEP point.
Yeah.
Is it recommendable or it acceptable working point of view? I'm asking. But we are not facing, even though we have selected the 50 to 60% of the pumps, we are not facing so much problems. Only if you have failures.
Yeah.
So why you are insisting for 80 to 120? Shall we go for 50 to 60% of the BEP? Is it accountable?
No, yeah. I think at 50, 60% you can probably, depending on the specific speed of the pump, you know, if it's a lower flow, higher head, you can get away with that. But on the sort of higher flows, lower heads, higher specific speed pumps, then they're they're more sensitive to running off best efficiency point. So again, it just depends the actual hydraulic design of the pump, you know. Pumps can run with sort of relatively low vibration at 50, 60, but they tend to be the lower specific speed pumps.
Okay, thank you. The last question. Actually, talk about the re-rating.
Yeah.
Re-rating. Actually, some of our main pumps are having issues due to the low flow requirements. Okay, we couldn't able to make. Actually, over-designed. Maybe due to the conceptual reasons, it was designed for some percentage, but we are actual utilizing is only 30 to 40% of that.
Yeah.
In that case, it is possible to change the impeller or not the internals. Change the internals and go for using the same pump, or we need to procure the low-rated pumps.
Yeah, Sanjit can answer that.
It depends what type of pump we are talking about. We are talking about single stage pump, multi-stage pump. Suppose, say, I don't know, if it is a multi-stage pump, then we need to check at the hydraulics available of that particular duty point which you are looking. If you are looking for reduction of the flow by changing the hydraulics is one of the solution. Destaging mainly we are doing if there is a reduction of pressure. Flow doesn't change much on that. But changing hydraulics or trimming down the existing impeller can give the solution for the reduction of the flow.
And the case study that was up, that was a 50% reduction in flow. That was the one Scott worked on for the North Sea just last year. Yeah, that was a Sulzer pump. So that was a big change in the hydraulics. So that's us bringing the best efficiency point down to sort of 40-50% flow. So it's definitely possible, and we've done it quite a lot.
Okay, thank you.
Parvila, Andre.
Yes, other questions we'll discuss during the talk. We sincerely thanks Mr. Callum and Mr. Sanjit Das for his insightful session. We are grateful for your deep dive into the complexities of brownfield projects and the engineering required to sustain legacy